In the last lecture, what you have observed is that we have done the Parseval's identity and how to find out the using the theorems, how to evaluate the integral value of the integral very easily, that we have seen in the last lecture. So, effectively the Laplace transform or Fourier transform we can use for evaluation of various complicated integrals and using the properties of them. Let us see the other example here. We want to derive the Fourier sine transform of f x, where f x is equals to 1 by x into a square plus x square, and then we want to evaluate the Fourier cosine transform of the function 1 by x square plus a square. So, basically first I want to find out the Fourier sine transform of the function 1 by x into a square plus x square. Then using that result, I want to evaluate the Fourier cosine transform of that particular function. Let us see it. So, effectively it is given to you, your f x is 1 by x into a square plus x square. This is given. So, Fourier sine transform of f x, which you can write down capital F s of alpha, and this is equals from definition you can write down root over 2 by pi 0 to infinity 1 by x into a square plus x square into sine of alpha x into dx. From the definition I can write down this thing, my function is 1 by x into a square plus a square x square. So, once I am finding out the Fourier sine transform, so I am multiplying by sine alpha x. So, what is your job now? Your job is to evaluate this complex integral, which is 0 to infinity sine of alpha x by x into a square plus x square. What you have done earlier to evaluate the integrals, you have used various substitution techniques, or by substitution we are trying to make it simple, so that you can evaluate the integral. Let me give you some other approach also for evaluation of this particular integral, so that I can use these results in the next section also. Suppose your I is equals to 0 to infinity 1 by x into x square plus a square into sine of alpha x dx. So, this is equation 1. Obviously, this is a complex integral, because if I can find out the evaluate this integral, I will know what is the Fourier sine transform of f x. In this case, since sine alpha is there, therefore, whenever I will make it, I hope you have done similar type of problems earlier also. Since sine function or cos function are involved, so if I use the differentiation under the sign of integration, then what I will obtain? If I differentiate this I with respect to alpha, you will obtain within the integral sign cos of alpha x. If you again use the differentiation under the sign of integration on that, that is double differentiation with respect to alpha, you will get back the sign. That is, you may get some ordinary differential equation involving I, where maybe d I square d alpha square minus some function of alpha, something will be there. So, we are going to use this particular approach here, because here the integration is under sin alpha. So, at first you differentiate 1 with respect to alpha, you differentiate 1 with respect to alpha. If I differentiate 1 with respect to alpha, d I d alpha is on the left hand side, and using the property, this will become with respect to alpha. So, x will come here, x cos of alpha x into x square plus a square into dx, because only it involves alpha term is involved over here. So, other terms will become 0, and differentiation of alpha is coming here. So, with respect to alpha, x cos of alpha x by x into x square plus a square into dx, the x will be cancelled and you can write it as cos of alpha x by x square plus a square into dx. So, this is equation 2, because I will use these things afterwards also. So, your di d alpha, this is equals to 0 to infinity cos of alpha x by x square plus a square into dx. Now, again in the next one you differentiate 2 with respect to alpha again. So, that di d alpha now will become di square d alpha square. So, again you are differentiating, this cos will become minus. So, 0 to infinity x sin alpha x by x square plus a square into dx, because your integration was actually your di d alpha was this thing, di d alpha was 0 to infinity x cos of alpha x by x into x square plus a square into d of x. So, once you are differentiating with respect to alpha, so minus x into sin of alpha x by x square plus a square into this thing. So, once I am getting this, so this equals, I can write down 0 to infinity x square multiplying both numerator and denominator by x. So, that x square sin alpha x dx by x into x square plus a square into dx. And once I am getting this equals, you can write down, this is your equation 2 we have written earlier, di d alpha. So, this equals, you can write down x square plus a square minus a square without loss of property, x square x into x square plus a square into this sin of alpha x will come here into dx. So, that you can write down this d square I d alpha square, this is nothing but minus 1 minus will come x square plus a square, this will be cancelled. So, that 0 to infinity sin alpha x by x into dx. This term, what was your originally your I was which one? Your I was this thing, your I was 0 to infinity. We assumed I is 0 to infinity 1 by x into x square plus a square into sin of alpha x into dx. Whereas, your di d alpha, that is di d alpha was this thing. So, once I am getting this, so from here d 2 I d alpha square, this is I have written as sin alpha x minus alpha into dx plus the term was minus minus plus. So, plus 0 to infinity a square by x into x square plus a square into sin alpha x dx. So, a square into given integral is nothing but this integral I, a square into 0 to infinity sin alpha x by x into x square plus a square. So, that you can write down this one as a square into I. So, I got this thing. So, this is equals a square into I, because this integral is this. So, this I am getting a square into I, and what is the value of this 0 to infinity sin alpha x by x dx? This is nothing but minus pi by 2. So, this again is known to me 0 to infinity sin alpha x by x dx, this is pi by 2. So, this value once I am getting pi by 2. So, this one. So, this value please note that 0 to infinity sin alpha x by x dx, this is pi by 2, which already we have done. So, effectively what is happening? you have to evaluate the integral, and for evaluation of the integral, you are differentiating it twice and ultimately you are obtaining one ordinary differential equation of second order, which I can evaluate very easily. So, you have the 1, you have the equation 2, these two I have to find out. So, effectively what is happening, you have this ODE d square I by d alpha square minus a square I equals minus pi by 2. Since here on the right hand side is not 0, therefore, the solution of this, there will be two components CF and the Pi. So, the complementary function, that is CF is equals to, it is simply m square minus a square equals 0. So, m equals plus minus a. So, that you can write down C 1 e power a into alpha plus C 2 e power minus a into alpha, because actually this is of the form m square minus a square equals 0. For the complementary function, you can find out this thing. So, it is m square minus a square equals 0. Just I am telling it in little details, if you have forgotten how to find out the solution of the second order ODE. So, CF you are finding out this, and the particular integral, that is Pi, this equals, you can write down minus pi by 2 by d square minus a square, d square minus a square. So, you can write it pi by 2 a square I can take common. So, 1 minus this minus I am taking it out. So, a square minus d square I am writing. So, 1 minus d square by a square to the power minus 1 of 1. So, this I am writing here. Now, I can expand this a minus x whole to the power minus 1. So, if I expand it, I will obtain pi by twice a square into 1 plus d square by a square plus, I am not writing other terms, because d square of constant will become 0 of 1. So, d square of constant is 0. So, I do not have to evaluate, write down further. So, this value will be simply 1 will come here, because for other terms will become 0. So, that you are obtaining pi by twice a square. So, you have obtained CF, you have obtained Pi. So, that you can write down your I now CF plus Pi. So, your I is equals to CF plus Pi, that is the solution of the second order ODE. Your CI is CF is C 1 e power a alpha plus C 2 e power minus a alpha, and your Pi is pi by 2 a square from the earlier one. So, this is your equation 3. Fine. Your I is this thing, please note this. Now, from here I have to find out the values of the constants C 1 and C 2. You have two parameters, two constants are there, C 1 and C 2. No conditions have been provided, please note that, because we are not supposed to evaluate the integral from this type. So, now I have to do some mechanism by which I can find out the value of C 1 and C 2. What is your d? So, this I have given as number 3. I can find out, differentiate 3 with respect to alpha. So, I am differentiating 3 with respect to alpha. If I differentiate 3 with respect to alpha, d I d alpha I will obtain, a will come over here, this term will be vanishing. So, if I take a common, C 1 into e power a alpha minus C 2 into e power minus a alpha, and this a is coming on both sides, this one becoming minus. So, this is your equation 4. So, basically now you have 1, 2, 3, 4, that is 1 is original I is there. If you wish, I can write down these 3, 4 are also there, and 1 is your given integral this. For your simple case, I am writing 1 by x into x square plus a square into sin alpha x dx. this was your equation 1 and your equation 2 was d I d alpha. This is equals to 0 to infinity cos of alpha x by x square plus a square into dx. This is your equation 2, this is equation 3, this is equation 4. Now, using these 4 equations, I want to find out the values of C1 and C2. You please see here, if alpha equals 0, then from 1 and 3, what you will get? From 1 and 3, whenever alpha equals 0, from 1 and 3, these two, you will obtain one equation, which gives from 1 gives you 0 equals from here 1 and 3 if I equate, because both are of I. So, in one case your I will become whenever alpha is 0, this side will be 0, your I is 0. Whenever alpha is 0, your I is 0. Therefore, you will obtain 0 equals C1 plus C2. From here C1, your alpha is 0. So, e power will vanish, C1 plus C2 plus pi by 2a square. So, you are obtaining one equation in C1 and C2, 0 equals C1 plus C2 plus pi by 2 a square. Now, if alpha equals 0, from 2 and 4 what you will obtain? In the same way, from 2 and 4, your d I d alpha, if alpha equals 0, your d I d alpha from here, whenever alpha is 0, 0 to infinity dx by x square plus a square, and this value is pi by twice a. Please note this thing, d I d alpha, this is equals pi by 2a. So, that if alpha is 0 from 4, you will obtain d I d alpha is pi by 2a, and from here you will obtain from 3. So, pi by 2a, this is equals to a into alpha 0 means e power will vanish C1 minus C2. So, now you see you have two equations in C1 and C2. These two equations, this is one equation and this is other equation. And if I solve these two, then I can find out the values of C1 and C2 very easily. So, you see by this way I am trying to find out the value of the constant C1 and C2. Once I is there, I am finding out d I d alpha, and original I and d I d alpha is known to me. From there, if alpha is 0, I am getting one equation. If alpha is 0, then from 2 and 4, I am getting another equation and I am writing this. So, by solving these two equations, I can write down, I will obtain C1 as 0 and C2 as minus pi by twice a square. And once I am obtaining this, then I is equals to pi by 2a into e power 1 minus e power minus a alpha. So, you see by this way I am evaluating the value of the given integral. So, Fourier sine transform of alpha or f x, if capital F of s of alpha is nothing but root over 2 by pi into I, and if you put the value of I over here, you will obtain root over 2 by pi by 2a into 1 minus e power minus a alpha. So, if I simplify this, I will obtain this one, root over pi is here. So, root pi again 2 is here. So, it will be root pi by 2 into 1 by this will be equals to, sorry, this is Fourier sine transform of this one, C2 is pi by 2 a square. Please note this. So, this will be twice a square, this will be twice a square. So, root over pi by 2 into 1 by a square into 1 minus e power minus a alpha. So, therefore, the Fourier cosine transform of the given function is nothing but root over pi by 2 into 1 by a square into 1 minus e power minus a alpha. So, by this way I am finding the solution. Now, what was the, just see here, if I, your function was this 1 by x into a square plus x square, I wanted to find out the Fourier sine transform. Then of course, this part till now I have not done Fourier cosine transform. So, let me just go through this thing once more, because this is little complicated and the evaluation of the integral process is also little different. I am just converting my integral in the form of ordinary second order ODE, and I am finding out the solution of that one. So, Fourier sine transform of f x, that is 1 by x into a square plus x square. This is equals root over 2 by pi 0 to infinity 1 by x into x square plus a square into sine of alpha x dx, which you have done earlier. So, I am assuming I equals this 0 to infinity 1 by x into x square plus a square into sine of alpha x dx, which is your given equation 1, because these equations will be important for us. We will use these equations again in the next subsequent methods, subsequent steps. So, once I know this I can always find out, differentiate both sides of the given equation with respect to alpha, and I can use the differentiation under the sign of integration process. So, d I d alpha you will obtain as I have shown you earlier 0 to infinity x cos of alpha x by x into x square plus a square into d x. And once I am obtaining this x will be cancelled. This is equal 0 to infinity cos of alpha x by x square plus a square into d x. This we are saying as equation 2. Now, again differentiate the equation 2 with respect to alpha on both sides of the given equation. So, that d square I by d alpha square I will obtain minus 0 to infinity x sin alpha x by x square plus a square into d x, because cos of alpha x this I am getting as differentiating with respect to alpha, I will obtain minus x sin of alpha a x, other term will become 0. So, d I square by d x, this now I am multiplying x by x on the numerator and denominator of the given integral. So, that it will become x square into sin alpha x in the numerator. This numerator now I am just writing as x square plus a square minus a square. So, that it becomes x square only. Now, I will break it into two parts. One part is this x square plus a square by x square plus a square will be cancelled. So, that in one case there will be minus sin alpha x by x into dx. So, this part is coming, and the second part if you see minus a square by x into x square plus a square into sin alpha x dx, which is nothing but I from equation 1. So, you can just check it. So, that this I can write down as minus 0 to infinity sin alpha x by x dx plus a square I, and this value of this given integral is known to us, that is pi by 2. So, that I will obtain a square I minus pi by 2, since the value of the given integral is known to us. So, I am obtaining one second order differential equation of the form d square I by d alpha square minus a square I equals minus pi by 2. So, there will be complementary, the solution of this second order ODE will be consisting of two parts, that is CF and PI. Complementary function will be, as I have told you, it has two roots, m square minus a square equals 0, the roots are a and minus a. So, that the complementary function simply I can write down C 1 into e to the power a alpha plus C 2 into e power minus a alpha, and the pi will be minus pi by 2 by d square minus a square. This I can write it as pi by 2 a square, from denominator a square I can take common. So, that pi by 2 a square and minus I am multiplying. So, 1 minus d square by a square to the power minus 1 of 1. Now, expand this series, If I expand it, I will obtain pi by 2 a square into 1 plus d square by a square, like that way it will continue. Since 1 is there, the differentiation, once differentiation is 0. So, d square, after d square by a square, I do not have to take any other term, because d square of 1 itself is 0. So, if I evaluate it, I will obtain the result as pi by twice a square. So, the value of CF I obtain, value of Pi I obtain. So, your I is equation 3, C 1 e to the power a alpha plus C 2 e to the power minus a alpha plus pi by 2 a square. So, I have now basically my next job is to find out the value of the constants, constant parameters C 1 and C 2. I have equation 1, 2, I have equation 3. Equation 1 is the integral of I, equation 2 is of di d alpha, equation 3 actual value of this, and this equation 3 I can again differentiate with respect to alpha, and I will obtain the equation 4. Once I am obtaining this 4 equation, put alpha equals 0 in 1 and 3, then from 1 your I will be equals to 0. So, that you will obtain 0 equals C 1 plus C 2 plus pi by 2 a square. Similarly, if I put alpha equals 0 in equation 2 and 4, I will obtain d I d alpha equals pi by 2 a. So, that the second equation I will obtain as pi by 2 a equals a into C 1 minus C 2. So, now you have two equations in C 1 and C 2, and these simple equations I can solve, and I can find out the value of C 1 and C 2. So, by solving these two equations, I will obtain the value of C 1 as 0, value of C 2 as minus pi by 2 a square. So, that the solution I equals, I can write down pi by 2 a square into 1 minus e power minus a alpha, and once I obtain I, then Fourier sine transform of the function I can obtain as root over pi by 2 1 by a square into 1 minus e power minus a alpha. Now, the next part is I have to find out the Fourier cosine transform. To find out the Fourier cosine transform of alpha, this is nothing but root over 2 by pi into d I d alpha, because your d I d alpha is nothing but this thing. D I d alpha, if you recall, this is equals 0 to infinity cos of alpha x by x square plus a square into dx. So, directly whenever I will write down, your function was 1 by x square plus a square. So, root over this, basically I am getting this one, your Fourier cosine transform of alpha equals root over 2 by pi 0 to infinity cos of alpha x by x square plus a square dx, and this value is nothing but d I d alpha. So, that I am writing root over 2 by pi into d I d alpha. You know what is I now? I already you have evaluated pi by twice a square into 1 minus e power minus a alpha. So, from here I can find out d I d alpha, and I can substitute. So, this will be pi by 2 a, 1 a will be cancelled into e power minus a alpha. So, that root over pi by 2, this will be root over pi by 2 1 by a into e power minus a alpha. So, effectively whenever I am trying to find out the Fourier cosine transform of the function 1 by x square plus a square, I do not have to do anything. Using the previous result itself, I am finding the solution, and I am getting the result as this one. So, for this part, I obtain the Fourier sine transform of the function as this. So, I am from here I am writing Fourier cosine transform of alpha is root over 2 by pi into d I d alpha, because d I d alpha is nothing but 0 to infinity cos of alpha x by x square plus a square into dx. So, this d I d alpha I know it from this I can find out d I d alpha, and I am substituting the value of this as root pi by 2 into 1 by a into e power minus a alpha. So, by this way, for evaluation of the integrals also, I can use the Fourier transform, Fourier cosine transform, Fourier sine transform and various properties of these transforms.